Hi, everybody. So I'd love to introduce Esteban Rossi-Hansberg from University of Chicago. And he's been looking at how the climate change is going to be affecting the society at large and hopefully what we can start doing about it. Welcome, Esteban.
Thank you. Thanks for having me. So this is so the paper I'm going to talk about today, or the work that I'm going to talk about today, is called "Anticipating Climate Change Across the United States," and it's joint work that I've been doing with Adrian Milal, who is at Harvard. So this paper or this project is part of a broader agenda that I've been working on for many years, trying to think about the impact of climate change, and in particular the local impact of climate change, how climate change is gonna affect particular locations, and then once you take into account that it's gonna affect locations differentially, so heterogeneously, then of course you need to think about potential adaptation mechanisms to climate events, namely, for example, through changes in the distribution of economic activity, as, for example, with mobility of people or different patterns of investment, so that the capital stock changes across locations. And so, throughout my career, I've been developing models of the spatial distribution of economic activity and the dynamics of the spatial distribution of economic activity. And so those are useful, we think, to think about the impact of climate change, because the impact of climate change is largely going to be about affecting specific locations and then how the economy is going to react to that. And so we need to model that forward and think about what are the implications of that for the functioning of the economy overall, and then for individual welfare. And so this is one of such models where what we want to try to incorporate in particular is extreme weather events. So the fact that heat waves or storms or floods affect particular areas, and then how does the economy react to those in particular, and then think about the fact that when agents are making their investment and mobility decisions, so think about someone in Florida that is experiences a storm, and then or thinks about the fact that storms are becoming more likely in their location, and so now it's deciding, well, should I move somewhere else in response to this? So what is the type of decision making that they're going to be doing? Well, that's going to depend on their perception of how the economy is going to evolve in the future, how the different parts of the United States are going to fare, how subject they will be to climate shocks in the future, etc. And so there's this kind of anticipation of what's going to happen in the future that they need to make in order to kind of decide where to migrate or where to invest. And so we want to incorporate that too in order to think about the overall effect of these heat waves and storms and the increased propensity of those as a result of the world warming up. Okay, so that's the exercise. And so what I'm going to do is I'm going to provide or propose what we call a dynamic spatial general equilibrium model of the U.S. economy, broken down in all its different counties, so 3,000 and change counties, and then model the effect of these climate events that I was talking about. Now that becomes a complex model because, like I said, think about agents in all these different locations that are making these decisions, and so they have to predict everything that is happening throughout the United States. And so that's a very, it's a model that has many state variables and many prices that have to be determined over time in the economy, and agents need to create expectations about that. And so that's kind of the complexity involved in this. And so part of this is trying to leverage some of the new techniques called kind of this master equation approach that my co-author has developed in some of his work as well. And so that's gonna be the main model. I'll show you the main elements of it in a second, and then we're gonna we need to quantify the model. We need to match it to the data, and so to do that, we're gonna estimate the damage functions, which are at the core of these models, using kind of long panels of climate events, the climate events that we've seen in the U.S. in the past. So we're going to use 100 and change years of those climate events, quantify the model, and that's going to then ultimately give us some implications of these shocks for the U.S. economy, and I'll talk more precisely about what those are in a bit. So the literature. Let me not dwell too much on the literature, but I mean, like I mentioned before, there's these evolution of models and frameworks, quantitative models, to try to think about the evolution of the distribution of economic activity in space and how different types of shocks affect that evolution, and by affecting that evolution, affect the performance of the economy and the dynamics of the economy. And so, in the last maybe 20 to 30 years, there's been a lot of progress in developing those frameworks, and also in matching those frameworks to kind of detailed local data. And so this kind of is definitely part of that effort, and it's taking a lot of advantage of that evolution. And then, of course, it matches with all the papers that have tried to assess or estimate the impact of climate change, or particular climate events, on the economy, which is kind of the some of the papers that are listed there under measure. Okay, so let me then go to the framework that we're using. And so now I'm gonna go a little bit more technical. So this is an economic model. The way these economic models in general work is we're gonna model different types of agents in the economy. There's gonna be workers. There's gonna be what I'm gonna call capitalists, and then there's gonna be firms, of course. And then I'm gonna put them all together in a model where I'm gonna have a notion of equilibrium prices that are determined as a result of all the actions of these different agents that operate in the economy over time. Okay, so the first type of agent that I'm going to describe are the workers. And these workers, they're going to live somewhere. In the particular application that I've been talking about, is going to be a county in the United States, one of these 3,000 and change counties. And they are going to have a problem, or the problem of the worker is going to be to choose their housing, their consumption, and a place to live, a location where they want to live. Okay, and so think about, and so this is expressed in this main equation that you see here. You see my pointer, right? I mean, this equation that you see here. And so what this is in the notation is there's some time discount that we call rho. Then there is a value function of an individual. So this is the welfare of an individual, the value of that the individual is trying to maximize, of an individual that is in some location I at some period t. And so this is the kind of flow value that this agent is getting. It's all in continuous time. So this is like a differential equation. And then, so at any given point in time, the individual derives utility from consuming goods, which are expressed by this C. So this is consumption. And then housing. So they consume goods and they consume housing. The aggregate, or the preferences of the individual, are aggregated through this simple power function, which in economics is referred to as a Cobb-Douglas function. And then And then there's some amenity associated with that location. So how nice it is to live in that location, some sort of general appeal of that location as a place to live. And this object, and in general, everything that it's in brown in these equations are things that can be affected by the climate shocks. Okay, so these amenities in a particular location can be affected by storms, can be affected in principle by heat waves, and so to the extent that they are, then agents are going to react to those because they affect the flow utility that they get from living in that particular location. Okay, so this is just the flow utility that the agents get from consumption of goods and housing, and then from these amenities. And then there's a component here, which is the change in the value that comes from changes in the environment or the economic environment in which the agent lives. And so that's going to be reflected as these changes in values as a function of time. And there's two basic components of this. The first is the fact that climate is going to be changing, or there's going to be this frequency of the storms and heat waves that is going to affect the system, and by affecting the system is going to affect the value for this agent. But there's also the fact that because there's these climate events happening, the whole distribution of economic activity is going to be evolving, right? People are going to be in different locations, potentially investment is going to, or capital and structures are going to change in the economy. And so the aggregate state, which is the whole distribution of employment and capital across locations in the United States, is going to be changing as well. And so that's going to be also in this kind of changes in the aggregate state, which is this expectation that you see marked there. And then finally, we have...
let me understand that thing. You're changing
Yeah.
the state and you expect it across all times or all agents? I guess are you
So
trying
this
to
is
optimize for more change or less change is what I'm confused about.
so this is so the economy is being hit or is going to be affected. Hopefully this is going to be clearer when I go to it's going to be affected by changes to the frequency of storms and heat waves in the different locations. That implies that agents are going to be changing their location decisions. For example, if some areas are more frequently affected by storms, that is going to in turn imply that the distribution of people, say in the United States, is different, and that changes the options that this agent has today and in the future of where to be, or how attractive it is to be in a particular location or another. And so that affects the continuation value of this agent, and that change in the continuation value of this agent is that term.
So
That's where
then
it's captured.
your value goes up when there's more change. I mean, from what I see in this equation.
No,
Or
well,
is
it doesn't have
V utility?
V is your value, your utility, your present discounted value of everything that you get. That's the object that you're trying to maximize. Yes.
And this sounds like, tell me if I'm got it wrong, is your V changes, assuming rho is positive, your V goes up when everybody's utility goes up? Everybody's change goes up. Faster motion means higher
No,
utility?
I'm not putting a particular sign on this object necessarily. This could be
Depends.
positive or could be negative. In particular, for example, if climate shocks become terrible, right? Then the change in value over time is actually going to be negative, right? It's going to affect you negatively. But the point is that it's all endogenous to how the economy adapts to these changes, right? So all of that object is here.
Got it. Thank you.
And part of this state is going to be affected by the next part, which is this decision. So these agents are going to have the option to move. And so they are currently in this particular individual that we're talking about is today in location I, and it can decide to move. And if the agent decides to move, but you know, in the next location is now going to get VJ. So suppose the agent moves to location J, then it's going to get this new value in location J. And then, but it has to pay migration costs moving from I to J. So that's going to make them not, you know, be not willing to move for any little thing, but I mean, you know, it's going to be costly for them to move. And then we're going to allow for them to have some idiosyncratic preference for the different locations. So, you know, you may want to move to a specific place because you have family there, or, you know, you like it for some random reason, etc. So this is going to be a random idiosyncratic preference that is going to come from some distribution that I'll specify later. Okay, and so the agent is going to try to create an expectation of how good it would be to move to some other location J. And so the flow in the value includes the fact that the agent has this option to move somewhere else. Okay, and sometimes the agent is going to use that option to move to another location. Sometimes it's going to decide to just stay put. And in that case, this term is going to be zero. Okay, and then this is all subject to the fact that they have to consume, they have to pay for consumption goods, they have to pay for housing, which is gonna be there's gonna be a rental rate for housing in every location, which is also again gonna be affected by the availability of housing in those locations, which in turn is determined by whether capital is destroyed by storms and for example, and then they receive a wage. And so they have to use their wage for consumption and housing. And for these guys, we're going to assume that there's no savings. So we're going to simplify the consumption savings decision. They use everything that they earn, they use locally, right? I mean, they consume, they use, and they live somewhere and they pay for housing. Okay, so those are the workers. And then we're going to have these capitalists. So the capitalists are the ones that are going to be investing. And so this is a very similar equation to the one I just showed you, but just for the capitalists, for these different type of agents. And so these capitalists, what they do is they are going to invest in capital, right? And this capital in turn is going to be used for production and for to build structures. I'll go through that in a minute. Okay, but they're going to invest in capital. And they're gonna consume. That's gonna be their flow utility. Then they're gonna invest in capital. So that's this I. That capital depreciates at some rate delta that is going to be location specific. So therefore depends on this I there. And this delta is kind of important. Why? Because that's the way we're gonna introduce these storms. So these storms, the way they're going to affect things is that they increase, or the way to think about them is they increase the depreciation rate of capital. So if you're in Florida and you're in an area that gets flooded all the time, that is receiving the storms all the time, then the way to think about this, when the frequency of these storms increases, that depreciation rate, that is as if the depreciation rate of the capital in that location increases as well. And so that's the way we're going to introduce those the effect of these storms. And I'll argue that does a good job in doing that. Okay, and so this is the investment minus, you know, the depreciation of capital. So this is the net investment. And then this is how the value of these guys changes when, you know, their capital changes. Then we have a term that is this aggregate state, and the changes in these aggregate states that also affects where these guys want to invest and the values of investing. And then this is the net savings of these guys. So they can borrow from other location at some interest rate. They get the returns from whatever their stock of bonds is, this B, their capital. And then we're going to add some adjustment costs of capital, which is this term here. And then and if you subtract their consumption, that gives you their net savings. And this tau here, they're going to get back some of the profits of the firms and some of the returns on rental on renting some of the property, and so that's all embedded in this DAO, so that the whole system is a closed system. And so one of the things to note here is these are the guys that are doing the consumption savings decision. They're deciding where to invest or how much to invest in a given location. Different guys in different locations are going to decide how to invest there, but they can borrow from other locations in order to invest locally. And so this is important because, of course, when some disaster happens at the local level, what you want is the local capitalists to be able to borrow from other locations and invest there rather than to kind of save their way into adding to the capital stock. So that's kind of an important element of this. Okay, so those are the two types of agents that we have. Then,
so a question. So
yeah.
you keep using the word agent, but from the equation, it looks like it's more like the counties are agents, where there's 2 agents per county, and these are rate equations saying what fraction, or I guess how is the representative capitalist or worker in a county faring, or how many of them there are. Is that about right?
Yes. So important. So these are two. This is the problem of an individual, and then there's going to be many of these individuals in every county, but they're all kind of identical, apart from these idiosyncratic terms that I was talking about, right? So that's going to imply that because the guys that are, say, leaving from a particular county in Florida to some other location as a result of the frequency of storms increasing in Florida, are not all going to go to the same location. They're going to be spread out, right, in a particular way, depending on their individual characteristics in terms of these idiosyncratic preferences, for example. So that all smooths the reaction of these agents across locations in a way that you can match exactly the flows that you see in the data.
And effectively, you're going to be modeling these as continuous, these people as continuous flows of population from county to county, or flows of capital for the investors.
Yes. So there's many of them, and these idiosyncrasies imply that I can think about this as a distribution across the different places.
Got it. Thank you.
Okay. And so these capitalists in a particular location, they're gonna save they're gonna invest in capital that's gonna lead to a capital stock in a given location. This capital stock is used to create buildings. These buildings then in turn can be used for housing or for commercial structures, which in turn are part of the production process. The same with labor. So there's going to be, these agents are going to decide where they want to live. That's going to lead to population in the different locations, and these workers can either produce work in production, in goods production, or goods and services, I guess, or they can build structures, right? So those are going to be the two types of jobs that we're going to allow them to have in this framework. And then the production function, or these are the firms that are going to be doing either the structures or the final goods production, are going to be modeled again as using these kind of power functions. So this is the amount of land in location I, the number of workers that are used for building structures, and then the amount of capital that is out there. That's going to lead to a certain stock of buildings in a given location. So you put some labor, put some land, or put some capital that leads to buildings. And then those buildings, like I said, are going to be used for either housing or commercial structures. And then these commercial structures plus the workers that are used for production, that implies once you multiply by Z, which is going to be the local productivity of the place that leads to total output in that location. And so this Z is again important. This Z is like what I'm going to be calling the productivity of a particular county, I, which is on average how good are the firms there in transforming inputs, which in this case are workers and these buildings, into, or capital structures into goods. Okay, so that's the, and so this Z is also being brown, meaning that it can also be affected by these storms and etc. Okay, and so now let's go to the climate damages. So part of an important part of these models, or a core part of these models, is how do you introduce the impact that climate has on these economic variables. And so there's, three main ways in which climate is going to affect the system of the economy that I just described. One is through these amenities in the worker problem. Another one is through this productivity that I just talked about. And the last one is through this depreciation rate that I mentioned as well. Okay, so there's these three components: the amenities, productivity, and the depreciation rate. That's the way in which whatever happens to the climate system is going to affect the economic system, that then is going to affect, the welfare of agents and the decisions of agents, or potential anticipation and adaptation actions of these individuals. Okay, so that's the way it works. And so the damage functions are at the core of all these assessment models. And so here is the way we're gonna think about them. So think about some global mean temperature T, right? That is think about some baseline temperature plus some innovation TD. So this is kind of the way, for example, people talk about this all the time is, there's some temperature, pre-industrial temperature, and then, these are the change relative to that. Okay, that would be the TD. And so it's the TD that is going to affect these economic variables. And the way we're going to introduce that, think about the case for depreciation. The other ones work the same way. So depreciation in some location I at time T is going to be some baseline depreciation for that location. And then that doesn't depend on T, it's just like the level of the standard level of depreciation in that location. And then, these blue delta I1, which is how changes in global temperature affect the depreciation rate in this particular location. And so the key object here is to determine what the delta is. How do changes in global temperatures affect local depreciation? Now that, of course, we could create another step, which is how does changes in global temperature affect local temperature, which in turn affects the depreciation. This is without loss of generality, right? Because we can go from global temperatures, map it to local temperatures, and then map it to depreciation, or just go directly. In this notation, we're just going directly, but it is without loss of generality in that sense. And then, I could have written this equation also for the Z's, for the productivities, or for the amenities, for the A's. It's exactly the same equation. I'm going to have a Z I1 here for productivity, and an AI1 for amenities, which are going to be the damage functions of how global temperature affects amenities, affects productivity. Okay, exactly in the same way. I just didn't write them here. Just gave you one as an example. Okay.
And these relationships are all linear.
And these relationships are all linear in global temperature, in this temperature.
In the delta.
Yes.
But in the difference, yeah. So just the limitation of this model is it's looking at small, not like mass exodus kind of changes, but like small linear kind of local changes in amenities and so on, right?
I mean, which can accumulate, and as they accumulate, they can have big effects, of course. But and in principle, as we're going to see, they will have big effects. But it's true that we're thinking about this as a small innovation in temperature, right, and kind of the effect that has on a small innovation in temperature.
So it would be good for like a Hurricane Harvey, like a Hurricane Harvey affects Texas, but or Houston, not hugely. But like a Katrina, or like devastated New Orleans, or Maria devastated Puerto Rico. So that's probably beyond the linear effect.
Yeah, I mean, but the way I mean, I guess the way we want to think about it is, yes, that there's a specific event that can destroy certain things, but then there is the change in the frequency of those events,
Right.
right? Which is really what's going to ultimately end up changing the system, not so much the individual event, but the
Right.
fact that the frequency of those events is changing, and that affects the full evolution
And
of the economy.
that's
So
going to
this
be a
is
more
really kind of
marginal.
a model of that, rather than a
Right.
model of the immediate reaction to a particular storm. I'll show you some of the immediate
Makes
reactions
sense.
to particular storms in a second, but it's more about that. Now, because at the end of the day, because was mentioning, this is kind of a complex system with all the state variables, blah blah blah. That implies that the solution mechanism that we're gonna use is gonna be a first order solution mechanism. So we're gonna approximate the solution of all that system to the first order in what I'm gonna show you today. You can do it second order as well, but today we're gonna do first order. And so because of that, this is without loss. I mean, that is, even if I had a second order term on this object here, I wouldn't capture it because of the approximation that I'm taking.
No, that makes sense. I mean, and always I'm also thinking echoes of all the agent-based people who point out that none of this stuff is in equilibrium. But then you have a lot of terms. They have even more terms to estimate, and so you always have this trade-off of the range of effects you can estimate versus can you actually estimate them.
Absolutely. So a big deal here is two things: is can you solve the evolution of the system, right? So that's the step number one, which is not easy. And then the second, and so that's where the approximation binds, right? That's where we're doing the first order approximation. The second is, to what extent can you estimate from the data the key elasticities that are going to govern the behavior of this economy? And for that, of course, you don't only need to solve the system, be able to solve the system, but be able to solve the system fast, right? So that you can really kind of iterate on parameters and search over a grades of parameters and essentially estimate those parameters properly. So those are
Makes sense.
those two. That's exactly the trade-off that you
Well, then I will
were
ask you
pointing.
later, perhaps, but just keep this in mind. What if you didn't care? What if you had infinite compute and worried about data availability, but not compute availability? Would your modeling approach change?
I mean, you can enrich it in that case, right? I mean, you can do more approximate. I mean, you can do, for example, if you had like infinite computer power, then you can solve this system without the first order approach. You can solve for the global solution of the system without approximation, and that would help. I don't think for the problem at hand that's that important, in the sense that I don't think that the global solution is that different than the one that we're finding here.
Right, makes
And
sense.
we've tried that in smaller cases, or you can try that by adding, say, the second order and comparing second order with first order and see how that system is evolving. And it doesn't seem that large, but of course, the more shocks you bring in, and the bigger the changes in those potential conditions created by those shocks, the more this is going to matter, of course.
Yeah, makes a lot of
So
sense.
that would
Thank
be
you.
the goal. But the data, but the data constraints, are significant, first of all. And the second is that, and this is, I should have probably mentioned this kind of more forcefully before, is it's kind of important to model the behavior of these agents and not simply extrapolate from past observations of this class of the behavior of these agents. That is, you can approximate some sort of impact of climate change and just extrapolate to the future, or you can try to think about how does this affect these agents, what are the decisions that these agents are going to make, and as a result of that, what's going to be the new configuration of this economy, which in turn, when a shock happens tomorrow, that's the economy that is going to be affected. That's the approach that we're following here, which we think it's important exactly because this is going to lead to circumstances in the economy that we haven't experienced, where extrapolating from past experience is just simply not very good. So
Right.
that's why we think that modeling here is important, right? Okay, so just to reiterate on what I was saying, so what's the complexity of this is you have these aggregate shocks, and then you have the distribution of employment and capital. These are the state variables. You have it in every county. So this is the number of state variables, and this is therefore the number of prices, which in this case are wages and rental rates, that you have to solve in the model at every point in time, and what these agents are making predictions over, right? And so that's the complication of these methods. And so that's where this discussion that we're just having is going to apply. So we're, in order to make progress on this, we're going to use these analytic perturbation methods that allow us to solve these models in first order or second order relatively quickly. And like I said, today I'm just going to show you first order. So there's going to be no risk component here. If you want to include risk, so that agents, think about the fact that now it's not only that they face on average, worse conditions if you are in Florida in terms of, the likelihood of experiencing a storm, but it's that you also value the fact that it's risky. So now it can happen sometimes, and you don't like that risk, right? And so that's going to also affect your decision making. That's the part that we're not introducing here because we don't have the second order in what I'm showing you. But we're working on that, and that's definitely feasible to do. Okay, so now so that's the model. How are we going to take the model and map it to data? Okay, so that's the next step. So we're going to use data, some economic data from census and BEA at the county level from 1960 to 2019, and then some historical climate data from this project here that we're going to aggregate at the county level. That's going to give us daily averages of temperature, wind speed, and precipitation, and that's going to allow, from there we're going to look at define a storm, which is going to be some threshold for wind speed and precipitation, define a heat wave, which is going to be some threshold for temperature, and then we're going to estimate first what is the empirical impact of those in the data, and then we're going to match them all to that. Okay, so that's the plan in what I'm going to show you next. And so the first thing is to think about when a storm happens, there's some event, right? What's the impact on economic variables? What is the observed thing? So this is, forget about the model for now, right? We're just going to go to the data and we're going to try to estimate this effect. What have we seen in the data, okay? And so the outcome variable here is this Y, which can be, local wages or local population, local investments. And then we're going to run this type of event study design, where D is some event that happened, so say a storm or a heat wave, right? And then this is the effect that has over time on this economic variable, adjusting for any sort of local characteristics of the place, time trends, then some local trends that are captured by these guys. So trying to saturate the model so you're not, confounding the climate event with other things. And so this is going to give us a dynamic response, right? Because this is I'm getting this gamma for different periods. Okay, so what do you find when you do this? So here I have storms and heat waves, right? And so think about a storm that hits a particular county in period zero here. So everything is normalized. So the event happens at period zero, right? There is nothing happens before. Obviously, an event happens at period zero. And then what does the data tell you is the effect of storms? Well, wages decline after that. So this is, over time, and they reach a negative effect of about 2% by year 2 or something after the storm. Okay, so that's what the data tells you. What happens to population? So population also comes down, and it all comes down a little bit more. So the max effect is about 4%. And then look at what happens to investment, which is interesting. You have a positive effect. So investment comes, so the storm comes, and then what happens to investment in the county? It increases, and then it comes back down. So what is this effect? So you can think about this effect that something got destroyed, obviously, as a result of the storm, right? And so investments pour in to the county in order to rebuild it properly, right? And so what this tells us is that the way, because of this pattern, so wages going down, population going down, investment going up, this can be replicated. This pattern can be replicated in the model that I showed you with a capital depreciation shock. And it's important that it's a capital depreciation shock and say not a productivity shock because of this effect on investment, right? Because if it was just productivity, so say, the storm comes and just destroys productive capacity, firms become less effective at producing, but it doesn't, you don't need to rebuild anything. Then of course what would happen is that you invest less, not more, right? Because this is not a good place to produce anymore. While if things get destroyed, you want to rebuild. And so the first action is to rebuild. Now, then over time, you may decide to invest less, but the initial impact is on rebuilding. And so that's going to happen when you have a depreciation shock. And so storms are going to, be mapped to depreciation shocks, because depreciation shocks is what generates this type of effect. And heat waves, on the other hand, we don't see any investment effect, right? We see a wage effect, we see a population effect, but we don't see an investment effect. And so what that means is that we're going to map that to like a combination of a productivity and an amenity shock. And we need the amenity shock because there is a little bit of an effect in wages, and this is significant. I don't have the standard errors here, but this is actually a significant drop in the red line here. But the effect on population is over time is quite large, and so that tells you that it can not only be productivity; it also has to be related to how attractive the place is as a place to live. Okay, so that's gonna push us to identify or to introduce the effect of heat waves as a combination of productivity and an amenity shock. Okay.
So question. Yeah. One choice you make here is your data set includes populations, but I was kind of expecting, given your spatially disaggregated analysis, you also have change of address forms, like do people move from hotter places to cooler places, or Phoenix to LA and no difference? Do you have that kind of analysis?
Well, I mean, so the characteristics of these places, right? Like the level characteristics of these places are captured in these type of regressions by these alpha i's and these delta I st, right? So this is already controlling for all the specific characteristic of this location and whatever that might do, right? So all of that is going to be captured already. And the fact that people move, there's a particular pattern of movement in the baseline, independently of the shocks or changes in world temperatures, etc., is also going to be, we're going to adjust the parameters of the model in a way that I'll describe in a second, in a way that it captures that baseline flow of people across locations. So the model is going to actually match that exactly. So we're going to choose migration flows and the rest of some of these parameters in order to match that baseline economy exactly right. So the model is exactly identified in the language of econometrics.
Okay.
on
So
that.
if I understand you
But there's
correctly,
enough flexibility to match that in the baseline. And this is all about then thinking about when a shock happens, what's the impact of that shock, right?
so if I understand you correctly, you're capturing the covariates of the out migration side, what kind of cities people are going from here, but it sounds like you're not modeling the where they're going to. Am I correct?
Okay, so we are. So this effect is just shock happens, what happens to local population or local employment in that location. So in that sense, you're right. This is not estimating, right? Where are these individuals going, right? I mean, it's not affecting or we didn't run this regression for the impact of the storm in one location on the flow of people from this location to some other location. If that's what you're saying, that's the answer is yes. We're not doing that.
Right, right.
Here is one reason. I mean, this is the limitation of this approach, which is that the data that we have over the time period that we have, even for these outcomes that are relatively aggregated, as you pointed out, right? It's is small. So you don't want to slice it too thinly, because then you don't find, then it's all noise, right? Because I mean, think about it. Look, people are moving because of all sorts of reasons from one place to another, right? And here comes these shocks, right? And these shocks, some of them are big, but at the end of the day, in the big scheme of things, they are not the most important effects on the economy. There's lots of other things that are happening to the economy. And so the first thing is you have to, and so that implies there's a lot of noise in what you see in the data, right? And so you have to tease out the effect that these particular events have on these outcomes, and that's hard. And so you want to do that on variables that are relatively aggregate in order to get some traction on the effects and be able to measure those effects. The more you thin, the more you slice it, the more noise relative to signal, if you will, and the harder it is to identify these effects, significant effects. And so
No,
there's
no, that's fair.
there's a kind of a limitation here on how much you can get from pure data from there. So here the approach in some sense is, well, let's use the baseline flows. Let's use this impact on these aggregate effects. Then we have a detailed model of how these people, evaluate these different options, and that's going to give us an impact on where they go. Okay.
So this actually makes a lot of sense. And then, yeah, the number of flows is, I mean, I've seen some of this data, it's enormous. Some of the decisions one might want to make, questions I have is, are people moving from rural to urban to rural, low tech to high tech, southern, hotter to colder? So if you slice the coarsely like that and do separate studies, is there enough data for that kind of analysis?
Yeah. So yes, definitely. So one of the things so if you do cold and warm, there's a little bit more traction. I should have said this. These are all reactions of storms already in a selected group of counties. So in particular, the effect that I'm showing you for storms is in inland counties. In coastal counties, because if I redo this exercise for inland counties, I get essentially zero, right? And the same for heat waves. This is the effect. The effect that I'm showing you here is for warm counties as defined above the mean on average. Then for cold ones, you can get a little bit of an effect also from cold waves, but essentially it's very muted. So we're gonna throw it out for this analysis that I'm showing you here. But absolutely, so you can start breaking things down and do it and use that to as over ID checks for the model. right? So we're going to use some, as I'll show you, but mostly these because that's where we get the most traction empirically, just from this kind of reduced form aspect.
Got it. Yeah, thank you very
But
much.
I mean, but I think there's a lot of limitation here in the sense that, of course, you can use one huge event and look at where people went, but that's also specific to that event and specific to that location. If you want to have many locations kind of in the general effect of these storms, right, then you need many of these events. And then a lot of these events are not as large, some are, and so that's where, I mean, I think this is kind of a crucial data limitation aspect, right? Just the fact that we just don't have that many periods and we don't have that many big events, right? I mean, by
Right.
definition, because we want to capture big events. I mean, it's also not like a small event. So big events are also, we're selecting them to be infrequent, right? Okay, so that's so now what's the estimation strategy? So the first part, so this is all about estimating the key parameters of the model and these damage functions. And I'm gonna, running out of time, so to be able to show you some results, let me go a little quicker. So the first thing is, if conditional on the data, which is going to be investment data, wages, population, amount of land in every location, and the full matrix of mobility across counties, right? So given this data and the parameters of the model, I can, in what's called invert the model and solve for the characteristics of the individual counties. So namely the baseline amenities, the baseline productivity, the amount of land is the same thing. And then this is kind of some investment, the cost of investment in every location. So these are the county characteristics in all these places. And I can solve also for the migration cost, which is a bilateral matrix across counties for all counties. Okay, so this is this, and you can, this is, if you count the equations and unknowns, of course, this matches, which means it's exactly invertible, right? So if you give me that data, I can obtain all these objects, right? And so that's going to guarantee that the baseline model that I put together exactly matches this reality, right? It exactly matches that reality. So the baseline point from which I can do contrafactuals is going to have the virtue that is exactly, and the reality is exactly the equilibrium of the model in the baseline. Yes. Okay, and then I need two key elasticities that I need to calculate, which is the migration investment elasticity. So this is when something happens, some change, say, in productivity or in amenities happens, how willing are people to migrate as a result of that? So if their wages in some other location increase, how willing are they to move? So that determines the migration elasticity, which is governed essentially by the dispersion in this idiosyncratic preference parameter that I was referring to. And so I need to calculate that investment elasticity, that migration elasticity, and then also the corresponding investment elasticity, which is given by the curvature of the investment function. And so these two, and so that determines when a shock happens, how flexible is the economy, how much does the economy react, right, to it. And so we're going to do that so that we match the population to investment response that I just showed you for heat waves, the population to investment response for storms, and the income to population response for heat waves. So these are three particular moments we're going to match. And so the way that we can do this is we can sample the model with different parameters, look at what is the response in the model, then compare it to the response in the data, and then, estimate these parameters for that. And so, for this you need to run them all. That's where the speed really matters, right? Because you need to run them all many times in order to be able to find the parameter combination that matches those moments that I just described. Okay. So let me keep it at that. That gives you some responses in the model that match the data, or at least are in the confidence intervals of the data, and that leads to a notion, or the implication is that like a storm, a 1 in a 50-year storm, is going to increase capital depreciation by 17%, and a 1 in a 20-year heat wave is going to, decrease productivity by 5%, and amenities by 7%. And then the final part of the quantification of the damage functions is to estimate, the changes in the likelihood of a storm or a heat wave in response to changes in temperatures. And so that you can just calculate from the data. So that's where we're going to leverage kind of the long panel in the data. And this is what we find. So for inland counties, in the case of storms, 0 essentially. But for coastal counties, we see big increases in the probability as a result of changes in global temperature. So a 1 degree increase in global temperatures now kind of implies an increase in the probability that goes from about 0.2% to about 0.8%, from 2% to 8%. So that's a big increase. And so that then together leads to the delta. So the change in the probability of the storm plus that 17% effect of a storm on depreciation implies, gives us the delta, the blue delta that we need to estimate. Okay, and so the same for again for productivity and for amenities. And so that gives you the damage functions. So here is a map of the US. This is just for you to get a sense. So 1 degree Celsius increase implies changes in capital depreciation only in coastal counties, because I limited it to that, right? That look like this, right? So, these are places that would, result in decreases in capital depreciation of about 4%, say there in Louisiana. And this is the change in productivity, which are broader because heat waves affect, all the, hot part of the U.S. And so you have all these negative effects here, particularly again in Florida and some parts of Louisiana and Georgia. Okay. So now let me show you what these all imply. So now we have these damage functions, right? So now I can do a counterfactual. I can say, well, suppose temperatures increase by a certain amount, how does the economy look over time relative to an economy in which that didn't happen? Okay, and I can compare those two outcomes. And so when I do that, I get losses for workers of about 5%, small losses for capitalists, and then, this is present discounted value. Why is that? Because, a lot of the impact is or most negative impact is going to happen more in the future. If I go to 2100 and I have a worker, standing there looking at the future, that worker is 11% worse off than without climate change. So this is kind of the level of facts that you get here, and these are corresponding to capital. And here I for capitalists, and here I broke it down through the different channels: capital depreciation, productivity, and amenities. And the point here is that capital depreciation, gets amounts for about half of the losses, and that's kind of so it's important to bring in this investment channel that I've been talking about. Okay, so one of the things, and so this is if you put it all together, and then I introduce climate change relative to not climate change as in the business as usual scenario of the IPCC, what would be the effect on the different counties in the US? So here is what you see. So this is the effect on welfare for workers, right? And so look at these numbers here. So it's very heterogeneous across locations. Some of these locations are going to lose quite a bit while some others are going to potentially benefit, or at least if you only consider these two impacts of climate change. There may be other impacts, of course, that are could also affect these other locations, but just from these two, you're going to have these negative effects in this area here, but positive and everything is blue. The positive effects are going to be relatively small, but the negative effects in some of these places are going to be quite large. And these are population changes. So population changes can be pretty dramatic, particularly in the coastal areas. So by 2100, a lot of this coastal area, according to this, is going to be fairly empty relative to what we see. And so just to give you a sense of magnitudes, in workers in Louisiana, where you get losses of about 10%, that's like losing $6,000 per year in those locations. So very heterogeneous effects, particularly concentrated in certain areas, and of course that makes people react, adapt to this by moving, and so that's what you see in the map on the right. I'll finish with two more things, and then I'm done. Is that okay? So
Please.
okay, so two exercises that may be of interest. The first one is the role of anticipation. So how important is it that workers understand that this is happening and that it's going to keep happening in the future, and that it's going to affect the different locations in the United States, right? And so of course, if workers, and so we're going to do an exercise in which we kind of eliminate that anticipation. That's again one of the advantages of having a structural model like the one I described, in which we eliminate the anticipation effects of these workers. And so essentially is like they experience climate change, they see that, and whatever happens in their location, they experience, but they don't understand that this is going to keep happening. They think that this is it, right? That the climate is not going to keep evolving in the future, right? So this is some sort of climate denial, counterfactual. And if that happens, of course, they end up moving a lot less. So this is the decline in the standard deviation of population changes relative to the baseline. So you see that, they move a lot less. So as a result of that, their welfare in the most affected location declines even more, right? So this is very bad, not realizing that this is happening and this is going to keep happening in the future implies that workers in some of these red locations here in the southeast of the US are going to lose about 2% more, or a little bit less than 2% more from climate change. So that's relatively large given the baseline numbers that I showed you. And perhaps interestingly, you get the flip side for capitalists, right? Capitalists kind of like workers not anticipating, because their capital is stuck in these places, right? They've invested already. They cannot move the capital. They can move investments to some other places, but they cannot move the capital itself. And so the structures are stuck in place. And so they don't want workers to move out. They want workers to stay in place, right? And so, keeping workers in some sense, not foreseeing climate change is beneficial for capitalists, all right? But these effects are large, and so that also emphasizes the importance of introducing anticipation effects. And then I'll finish with this. This is about migration and the importance of migration as an anticipation effect. So the first thing is that, of course, as this happens, and workers are negatively impacted in certain locations, both because capital is depreciating, because amenities are declining and productivity is declining, they want to move out. And so what if we eliminate the ability of them to move out? Well, then, of course, in the areas, the most affected areas, that's really bad for them, And so that implies in the Atlantic coast here, about a 15,000 extra loss per year for some of these workers. So this is huge, right? So the ability to move is essential as an anticipation mechanism to eliminate the cost for or reduce the cost for the workers that are in the locations that are most affected. Overall, for the United States, is not such an important, and it doesn't reduce the overall cost for the United States. Why? Because the overall costs are determined by whether the new allocation where these workers go is a better allocation than the past allocation. And that's specifically related to the correlation between the value of living in a particular location and the likelihood of that location being affected by climate change. And so if the shocks coming from climate change are very highly correlated with places that are very valuable, right, then that's in general bad, because then migration is bad because it makes people move away from the most valuable locations, right? If you get the positive correlation, then migration is good. And in the US, just happens to be the case, and this is just specific to the US, that that correlation is about 0. So the places that are negatively hit by climate change are neither particularly good places or particularly bad places. They're kind of average places within the US, and that implies that migration as an adaptation mechanism in the US has aggregate implications that are very muted. While for specific locations, of course, they are huge, as I emphasized. This is in the other work that we've done for the world as a whole, that this is not the case at all. Because in the world as a whole, climate change affects mostly places that are not so good in terms of the economy is not as productive, etc. So there's economies that are not as advanced technologically and in terms of amenities too. And so what that implies is that moving people out of some of these places is not necessarily such a bad thing. And so migration helps a lot. And so migration actually reduces the aggregate losses from climate change in the world significantly, while in the US.
So actually, on that point, is it within a country or across countries? Because across countries, that wars start that way.
That's both. It's both within and across, and it depends a little bit on what type of thing we're talking about. When you think about climate change overall, because it's so correlated across locations, right? I mean, unless you are like a huge country like China or Russia or the US or Brazil, right? Or India, the local adaptation possibilities are not that large on average, right? Because, the whole country is going to warm up, right? Now, of course, when we're talking about like coastal flooding, etc., then or this type of storms, that's much more localized, and so then the local adaptation becomes much more important. But if we think about the overall average level effects from warming up, what you see is that all these places or many of these countries the whole country is going to warm up, and so many of the locations of those countries are going to be affected by the increase in temperature, and therefore the main adaptation mechanism is to move out of the country, not out of the location, right? But still, migration becomes a big important adaptation mechanism for the world. And of course, that depends on the migration restrictions. If migration restrictions are extremely restricted, or migration frictions are extremely high, then you cannot use that mechanism, and so that is going to imply higher costs from climate change, right?
Right. And then one more question. You called them workers and capitalists, but really it sounds like in your model, it's mobile individuals versus immobile. So homeowners are partially capitalists. Financial investors are highly mobile. They're more like workers. So how does it affect different kinds of people?
Yeah, no, interesting. So the point here is true that the workers can move, So those are the guys that are adapting my moving, right? And then there is the investors, which it doesn't matter really where the investor lives. What matters is that this is an investor that is investing in some county in Florida, right? And so to the extent that this investor is investing in county in Florida, has some capital there, and that capital is stuck there, right? Now, because that investor can borrow and lend from everywhere in the world or everywhere else in the United States, it doesn't matter where they are so much. What matters is that their investment is stuck there because, it's brick and mortar buildings and things that are stuck there, right? And so that's the part that matters. That
Got
there's
it.
some component of these decisions that is not as easy to move around, right? Or another way of saying it more precisely is that you can move the flow, the investment, right? But you cannot move the stock, the capital itself, right? And so the only adaptation mechanism in that case is to move the flow, right? To invest in a
It makes
different place.
sense.
Yeah.
Right.
Okay. Okay. So that's what I got. Sorry about going over time a little bit. And so what did we do? Build a quantitative dynamic spatial model for these 3,000 US counties. We introduced these storms and heat waves, and then that allows us to analyze their effect and the adaptation effects both on migration and capital. The basic methodology can be, of course, used to do all sorts of climate shocks. One big issue is to map changes in temperature to these local climate events. And so we've done that for storms, and we've done that for heat waves, but it can be done for all sorts of other implications of climate change, and those can then be relatively easily introduced in these type of frameworks. Similarly, one can add more complex descriptions of the economy. For example, add different sectors where where the productivity of the sector is affected differentially by sector from storms and heat waves. So there's some evidence, for example, that agriculture is more affected than manufacturing, or that construction is more affected than certain services. And so you can bring that in. The big constraint of that is, like we discussed before, the estimation of those damage functions, right? What is the fraction that we have in the data to estimate those damage functions, properly, in a way that is general for the whole economy, and not, one particular event in one particular location? Because of course that the impact of one particular event in one particular location can be very specific to that location. So if we want these deltas in the notation that I was using, that are location by location, right? You need to estimate them from events that happen in many locations, right? So that's kind of a key bottleneck. And then the last part is, of course, I've been talking about average effects, but these effects there's large uncertainty about the path of climate change, and how climate change, and in particular temperature increases, are going to affect these specific implications of climate change, namely the storms or the heat waves or coastal flooding or whatever other impact you want to bring in. And so bringing in that risk and thinking about how agents are going to react to climate change, once you acknowledge that they understand that this is very risky and that this is nothing is set in stone, etc., and whether that's going to make them react less or react more, etc. And so that's important to understand individual reaction, but it's also going to be very important when you use this type of frameworks, which, and this is an important use of them, to do policy, to design good policy that taking into account all this type of adaptation. Anyway, thank you.
Yeah, thank you very much. It's fantastic. And thank you for taking the extra time.